This is an air monitoring device I built to monitor my Voron 3D printer's environment right here in my room. Before this, I used a consumer-grade monitor. But once I built my own filtration system, I started questioning its VOC sensor. It barely registered the heavy smell of printing ABS. That's why I sparked this new project. After several months of research, design, and fine-tuning, here is my custom air monitor. I designed it to run on its own dedicated web UI, making it incredibly easy to keep open in a browser tab, sitting right alongside your main cell dashboard. Beyond 3D printings, I have an even better plan for this hardware. It needs to be highly reliable, fully independent of any proprietary smart home ecosystems, and ready for multi-room deployment. My goal is to gather raw data for deep analysis to optimize my indoor ventilation plan, like experimenting with fan placements to achieve perfect air circulation throughout the house. To ensure long-term reliabilities and cost-effective maintenance, I chose 3 premium individual sensors, the SPS30, SGP41, and SCD41. Using separate sensors means that if one fails or gets degraded by heavy pollution over time, I can replace just that single module instead of the whole unit. Best of all, they all communicate over a clean, simple I2C bus. These 3 sensors track for particulate matter sizes, VOC and NOx indices, CO2 levels, temperatures, and humidity. To display all of this clearly, I divided the screen into 10 distinct cells. To give you an instant at-a-glance status of your room, HeatRisk parameters feature a color code warning system. Each risk parameter has 4 color states, complete with precise values and a scaling meter. The final cell displays the device name and Wi-Fi connection status, which is incredibly handy when setting up the web UI or calling APIs for external data processing. On the hardware side, the brand of the device is a standard 30-pin ESP32, paired with sensor breakout modules and custom 3D printed housings. For the screen, I opted for a wide-angle IPS TFT display. My first prototype used a standard TN display, but the viewing angles were terrible unless you look at it straight. The ESP32 and all modules plugged into a custom adapter board. This layout serves 2 critical purposes: thermal isolation and EMI protection. The adapter board acts as a physical barrier, splitting the internal space into front and back chambers. The front side houses the TFT display, the ESP32, and the MCP 1700 bar regulator. Grouping these together isolates the heat output from the sensors, preventing temperature drift. The backside is dedicated entirely to the sensors and a socketed Type-C breakout board for power. To shield our I2C and SPI signals from Wi-Fi interference, the adapter board features large double-side ground ports for bus EMI protection. I also use several ceramic capacitors for noise filtering. I deliberately avoided electrolytic capacitors here. Ceramic capacitors have no polarity, are highly durable, and are much easier to source and replace, making future repairs a breeze. To keep things DIY friendly, every single component on the board is through-hole. The enclosure consists of two main 3D printed parts. The front housing includes the TFT display frame and the mounting slot for the adapter board, and at the back it holds the Type-C breakout board and fastens to the back mesh housing. For the aesthetics, I wanted a sleek, clean look. The exterior is printed in PETCF, showing off its gorgeous, unique matte texture with absolutely zero visible screw heads on the surface. Ventilation is a key for an air monitor, so the back cover is almost entirely covered in a hexagonal mesh. The adapter board acts as an internal baffle, routing just a small portion of the airflow to the front heat-generating components, while leaving the vast majority of the ventilation dedicated to the sensors. I also added heat dissipation slots along the top, and designed two small utility parts, an SPS 30 basket and an upper bracket to secure the adapter board. Let me show you how this all comes together. Starting with the front housing. First, I press the TFT display straight into the frame. Because I designed this with tight tolerances, I have to apply firm, even pressure to snap it perfectly in place. Once it is seated, I secure it with 4 screws and plug in the cable. To save myself some headaches down the road, I custom create these wires with different colors so I can verify the orientation at a glance. Red, of course, goes to the display's VCC. From there, I pre-assemble the adapter board with the sensor breakout modules. To make the installation bulletproof, I printed all the module and PIC names directly onto the PCB seal screen. Before I slide the adapter board into a slot on the front housing, I give the display cable a wide, gentle bend and plug it in first. I actually designed a dedicated notch on the edge of the PCB, just to give this cable the perfect amount of clearance. Once the board is in, I secure the bottom with 2 screws and lock the upper part down with the bracket. Next, I grab the Type-C breakout board. I mount this with the connector pointing downward and fasten it with 2 screws to create a really solid physical anchor. I specifically chose a breakout board with 2 5.1K ohm pull-down resistors here. If I hadn't, the device would only accept A to C cables, and I wanted to make sure I could use a standard USB C to C cable to power the whole thing. Once the breakout board is secured, connect the power cable running from the Type-C breakout to the adapter board. For the rear housings, I start by installing the SPS 30 basket, making sure the notched edge faces the correct way. I secure the basket with 2 screws, plug in the sensor side connector, and press the SPS 30 right in. The datasheet has strict guidelines for placing this sensor, so I engineered friction-fit corners inside the basket to securely grip the sensor and prevent it from slipping out. For the final merge, I plug the other end of the cable into the adapter board. As I slide the rear housing onto the front housing along these top rails, I carefully guide the cable so it sits safely between the TFT display and the ESP32. During this sliding action, you will feel the adapter board's upper bracket engage perfectly with the SPS30 basket. To lock everything down, I use 4 screws, 2 at the bottom to hold the housings together, and 2 to tie the upper bracket to the basket. I always make sure to tighten these 4 screws evenly, which relieves any mechanical stress on the 3D printed plastic. For the firmware, I developed a robust web server architecture. When powered on, the device checks for safe Wi-Fi credentials. If found, it connects automatically. If the connection fails or no credentials exist, it clears the memory and boots into access point mode. From there, you can use any device, usually your phone, to connect to the hotspot named SE Air Monitor, followed by a unique ID suffix, which is displayed in the screen's final cell. Once connected, simply select your home network, enter your password, and the device will boot onto your network. The TFT display will then show the exact IP address assigned by your router. Here is a quick system diagram showing how this network communication flows. By typing the device's IP address into any browser on the same network, you will open up the custom web UI. This dashboard displays the current sensor readings with their matching risk colors, high-resolution 2-minute live histories, polling every 2 seconds, and 24-hour trend charts. The left column mirrors the real-time data on the physical TFT screen. The middle column captures fast, real-time environmental events with 2-second interval polling. The right column displays the 24-hour trend. Unlike the live charts, it takes those 2-second readings and plots their 5-minute averages. This does an excellent job of filtering out temporary noise to show the true trend of your room over time. All of this data is accessible via 3 simple, clean JSON APIs. API for current values, history for the short-term live data, and long for the 24-hour trends. The long API also includes maximum and minimum values that are plotted on the web UI. I also map the risk threshold colors directly under the line charts to make visible analysis intuitive. Because these return standard JSON, any smart home hub or custom script can easily parse them. And here is the best part. You don't need to run Home Assistant or any complex smart home server just to use this device. It works completely standalone with a simple Wi-Fi connection. But if you do use Home Assistant, these lightweight JSON APIs make integration incredibly simple. This provides zero ecosystem login while maintaining the flexibility to connect it to an existing setup. I spent a lot of time optimizing and tuning this web UI. To keep everything perfectly fluid, the three APIs share data updates every 2 seconds, ensuring smooth chart transitions. To optimize bandwidth, the 24-hour trend normally updates at a lower 5-minute rate when active. However, if the page has been idle and you wake it up, the UI enters a turbo mode to quickly fetch and stitch together any missing data points. This is much faster than making you wait 5 minutes for the charts to catch up. I even added a dedicated progress bar so you can see the backfill process in action. To run out the user experiments, all charts feature dynamic y-axis scaling, showing minimum, maximum, and average for the period, and an interactive cursor to pinpoint specific historical data points. Initially, I wanted to feed these sensor readings directly into Moonraker and display them on the Memcell dashboard. But after diving into the integration, I realized that Clipper and Memcell are natively designed to display complex, multi-parameter air quality data cleaning. Forcing it into that ecosystem turned out to be clumsy and unintuitive. That's why the standalone web UI is such massive advantage. Instead of wrestling with Clipper configs, you can simply keep this web UI open in a browser tab right next to your Memcell tab. It's a much cleaner, more straightforward workflow. The two systems run completely independently, meaning this monitor can gather high-density data without ever touching your printer's resources or affecting Clipper's operations. Now, some of you might wonder why I didn't include a dedicated high-precision SHT4X sensor for temperature and humidity. Technically, the SGP41 gas sensor does require real-time temperature and humidity data for its VOC and NOx compensation algorithms. However, the onboard SCD41 already provides these readings directly. While adding an SHT4X sounds better on paper, the data stream from the SCD41 is already more than sufficient for the SGP41's compensation algorithms. To explain why I omitted a separate SHT4X, we have to look at it from two perspectives. First, the sensor's perspective. The SGP41 needs to know the exact temperature and humidity of the microenvironment immediately surrounding its own package. Without this local baseline, its VOC and NOx index calculations would drift as moisture fluctuates. Since the SPS30s and SCD41 rely on their own internal sensors anyway, I placed the SCD41 directly next to the SGP41. This perfectly captures the actual microclimate that the SGP41 is breathing. Second, the user's perspective. As users, we want our screen to show the macro room temperature, not the warm microclimate inside a plastic enclosure. FT electronics generate heat. Display the true room temperature, you will have to program a temperature offset. But here is the catch. Fixed software offsets easily fall apart in the real world. They change completely depending on your enclosure design, where you place the device, local drafts, or stagnant corners. Under shifting environmental conditions, a static offset is useless, even if you are using a hyper-accurate sensor like an SHT-45. That is why I chose to feed the SGP-41 the raw, uninterrupted microclimate data it needs from the SCD-41, and display those readings as is, rather than relying on arbitrary software offsets that fail in real-world scenarios. This is where the project stands today. There is still plenty of testing to do, like optimizing the enclosure geometry to minimize heat buildup, and conducting thorough sensor validation. My next step is to build a second prototype, place them side by side, and analyze learned data deviation to ensure reliability. Thanks for watching, and keep moving forward.